All right, guys. Week 10. Can you believe it? Fastest quarter ever. Yeah, so we're coming down to I don't know what you want to call it. Is it the wire? Sure, we can call it we'll call it the wire. Coming down to the wire. And I think that hopefully you guys are just managing the world, managing your life, feeling good about things, feeling good enough about things, we'll say, and kind of have seen, kind of have a sense of where we're headed in this class. I'm excited for kind of this last week here. I think this last stuff is really cool. And kind of you guys have already seen it a little bit in your lab, but ultimately I think that seeing it in lecture will kind of make everything come together nicely. So I don't know what's going on. There we go. So what is up on the horizon? Well, I posted lecture quiz 6, and that will be due next Wednesday, which is the day of the final exam. And yeah, the finals at 8 a.m., right? So what I'm going to do is I'll probably extend the time again, just so my intention is to keep it at roughly the same length as the midterm, so you guys don't actually need all that time. But I think what I'll probably do is just make it from 8 to 12 or something like that, and so everybody has more than enough time. And so if you slept until 8:30, 9 o'clock, you're not in trouble by any means. And I'll have more information about that on Thursday when I have a better sense of how far we get today. Because as you guys know, I don't want you to. I'm not going to have you responsible for anything that I don't cover in lecture. So you may see some questions that are maybe beyond what we covered, and those are just informative, and can help you prepare for the future, especially if you're taking 108, because really these last few weeks, especially this panel data stuff is not something that's typically covered in Econ 107. So if you're going to take 108 in the spring, you're going to feel really ahead of the game for about 2 or 3 weeks, because we're going to do panel data to start the entire term. So we won't have the stats review like we had when we started this class, but we'll have essentially our regression review will be log regressions, and then this the panel data here that we're going to talk about. So and then the final exam, you can think of it as stuff from the entire quarter, but it's less so. I'm not going to ask any stats questions, and then I think everything else just kind of builds on itself for real. Like, this isn't just like kind of building on itself. Like, I'll ask you about interpretations, and asking you about interpretation of just a basic regression is actually probably welcomed, relative to what we're seeing kind of more recently, with something like a log regression. So I would just think of it as everything except for the stats review, but also think like, if I have an opportunity to ask you about interpretation of a log regression, like that's probably what I'm going to lean towards more than just an initial y equals beta 0 plus beta 1x. So, but yeah, that's really the continuity there. Expected value of u given x, that's going to come up again today. Came up last class, so that's not necessarily going away, but yeah, it was one of the assumptions too. So it's just been with us for the entire quarter. So, all right, let's see. Lab assignment 5 is due on Saturday. Lecture quiz 6, final exam Wednesday. That's what we got. So I've got problem set posted. I told your TAs kind of you got multiple sections this week. It's really just all review. There's no more like lab sections. So just it was the final at 11:30. So can somebody confirm that? Maybe I'll just look it up here. UCR final exam schedule. All right, I'm looking this up right now. This is straight from the fall 2021, Thursday. What time is it? 2 o'clock. Wednesday, December 8th, 8 to 11. I wish I made the rules. So, but at any rate, I will. You guys have more than enough time to do that. So, yeah, more information on the way. So, but let's get rolling for this last week. Like I said, I really enjoy this material. We're going to be talking more. We're going to be bringing state into this. This will probably help you with your labs. and then really again catapult you into 108 if that's where you guys are headed. So okay, so what did we talk about last class? We talked about the diff and diff estimator, the difference in difference, and so we looked at Lyon County and Churchill County, and we looked at that cluster of cancer outbreaks in Churchill County and how that affected the housing prices. So I had to update the syllabus. That's on me. The newest syllabus says the 8th from 8 at 8 a.m. So that was on me. 9th, if you do want to take the Econ 2 mid final, that's at 11:30. So yeah, let me know if you want to do that. But yeah, last class, what we saw, we predictably saw this reduction in housing prices when there's this big health risk in Churchill County, and we saw that shock was not only just the nominal shock in Churchill County. I think it was 4%. But then we also said, well, how much did prices change elsewhere? And the prices actually rose elsewhere. So that net change, or that difference in difference estimator beta 3, right, was 7.7%. So that there was a reduction of 7.7% in housing prices in Churchill County after this outbreak. So that really lends itself to a nice, I think, straightforward regression that's introducing a time element that we haven't had before. So if we looked at what we ran last class, we had housing prices in a particular county I at a particular time t, and we just had before and after. That was regressed on beta 0 plus beta 1 times whether you're part of the treatment group. So whether group I was part of the outbreak or not. So we just had a dummy variable essentially for Churchill County. And then is it after the outbreak or not? And that would be T, subscript T, right? So that time element comes in there, and that's just a dummy variable for before and after. And then we just had beta 3 times that interaction saying, well, what's going on in Churchill County after this outbreak? And so beta 3 is one estimator give us that net difference, which is, I think, really helpful. Now to kind of just jar the memory and think back to this, right? This regression led to, in this, we'll say binary times binary interaction regression leads to the average in 4 different groups. And so that first group of 0 and 0, right, before in the non-treated group, that average housing price was beta 0, right? If we look at how that changed over time, it went from beta 0 to beta 0 plus beta 2, and we would say that the difference then is beta 0 plus beta 2 minus beta 0, which is equal to beta 2. So the difference, right, from going from time period 0 to time period 1 for our control group, or the group equaling 0, was beta 2. That's what that beta 2 coefficient told us. Similarly, right, if we look at that before time period, and we say, well, let's look at group 0 to group 1, the control versus treatment. Well, the difference between those two is going to be beta 0 plus beta 1 minus beta 0, which is just beta 1, right? So we can go ahead and say the difference kind of before anything happens is beta 1, right? But then the difference of group 0 from the time period 0 to time period 1 is beta 2, right? We can do the same thing, right, when we go to these other dimensions, or kind of the second row and second column here, right, and say, well, what's the difference, right, in group 1 for before and after, right, for before and after? Well, we would say they ended up at beta 0 plus beta 1 plus beta 2 plus beta 3 minus beta 0 plus beta 1. That's where they started. So Churchill County started at beta 0 plus beta 1. We ended up at this big set of numbers here, right? Because we have 1, 1, 1, 1, right? A bunch of ones here, right? So the difference then is going to be beta, we're going to say beta 2 plus beta 3. So think about what this is saying here, right? So we've got 2 groups, right? 2 time periods. The difference in group 0 in time period, from time period 0 to time period 1 is beta 2. For group 1, in that same time period, it changed by beta 2 plus beta 3, right? But then when we look at time period 0, right, that difference between the 2 groups, beta 1 here, but then when we look at it in time period 1, right, in the treatment period, well, we ended up at beta 0 plus beta 1 plus beta 2 plus beta 3, subtract beta 0 plus beta 2, end up with, well, we've got beta 1 plus beta 3. So what we've seen here is we've seen a lot of differences, right? And that's what I'm trying to expound upon you here, is that we've got these 4 groups. They differ both in terms of just the grouping itself and then the time, and then we can go ahead and have multiple time grouping changes or differences. And so that difference, right, here's a beta 2 difference, a beta 2 plus beta 3, here's a beta 1 plus beta 3, here's a beta 1. If we take the difference of the differences, well, what do we get? Well, here we can say we started at beta 2, we ended at beta 2 plus beta 3. That means that if we take the difference of the difference, we get beta 3 right there. The same thing here. We can say, well, we have a final difference of beta 1 plus beta 3, but if we subtract where we started at beta 1, we end up with beta 3. So the reason I like to just talk about this, and this is, we went over this in kind of more detail on Tuesday, but I like that we can essentially show, it's like a big puzzle, and we can show where the difference and difference estimator ultimately comes from, right? Because it's just taking the difference of those differences, literally, right? It's literally taking those differences of those differences. We saw it graphically, we saw it with a regression, we did see it with a table in those numbers, but I think it's nice to be able to say more generally, right? We can always count on beta 3 being this difference and difference estimator, okay? So that's ultimately where we ended class last week. Now, I didn't talk about it quite in this context, right? Again, we had more specific numbers to go on, but we can go ahead and you can kind of back out, right? Go backwards and say, okay, well, which numbers went where when we run that data? And all comes right here, right? We had the 11.5. You might remember these numbers, right? So there's our difference, 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 and difference right there, okay? So what I like about this, though, and I think this is a nice transition, is if you think about just the whole journey we've been on, right? We went from saying, okay, linear regression after the midterm, right? That might not be the best way to fit the data, so let's go to these nonlinear regressions or log regressions. But then there's also concerns with that, so let's go with interaction terms. Lots of ways we can run those regressions. Now we can say, well, that still might not fix our expected value of u given x equaling 0. So let's see if there's an experiment out there that can potentially separate these groups into treatment and control groups in a natural way. And that's what we saw here. And we can just go right back to that interaction term, right? Interaction regression. Now, the thing that this really did is that this panel, or this difference and difference estimator, allowed us to bring up a time dimension, right? A difference in difference, right? In this context, right? So when we had the cancer outbreak, right? This introduced a time element. Right? This introduced a time element. And this will essentially leap us forward into panel data, okay? And so this is going to be the last topic that we're going to have. But again, if you're taking 108, we're going to come right back to this, and this is essentially where we're going to launch from. But panel data has a strong connection to what we've just done here, because panel data is specifically observations on multiple entities. So when you think about entities, we're thinking about individuals, right? That would be one type of entity. We could also have districts, like school districts, states, etc., right? So that's what we can think of as entities. And each entity is observed for 2 or more periods. Okay. So we're able to look at a specific state, right, for more than 1 year. Or we could say, let's go back to our original. We're not going to bring up this data anymore. We're going to look at a new data set. But imagine we have our 420 California school districts. and we observe them for 2 years, right? 1999 and 2000. So then, right, because if you think back to that data, right, we had just like a list of 420 California school districts. We just had it for that one single year. Well, now let's imagine we have it for 2 years, right? So then we would have 840 observations. 840 observations. So we could. That's one example of panel data, and I'll show you guys these kind of hands-on in just a second when we go to the data set we're going to use for the rest of the week. But you could also have what you saw with my work that I brought up a few weeks ago. I had 50 states. I observed them for, I don't know, 15 years or something like that, but you'd observe them for 3 years. So in that case, you'd have 150 observations. So what panel data can do, and this isn't necessarily a good or bad thing, it's just a factual observation, is that if you have multiple entities and you observe them for more and more years, your observations are going to go up pretty significantly and pretty quickly. So you got 1,000 people that you observe for 20 years. That's an awful lot of observations. The most recent paper that Bray and I are working on is on student evaluations, and she's so good with the big data sets. And what we have is we have all the student evaluations at UCR between 2013 and 2019 for every student. So the data set is 1 million observations. And it's not good or bad. It's just there's a lot of observations, and so it's more that it takes a lot of processing power as opposed to actually feeling like the data is cumbersome. And I'll show you how that kind of translates in just a second. So okay, so when we describe this type of data, right? When we describe this type of data, right? What we're describing is some sort of independent variable that's changing along 2 dimensions now, right? It's changing based on the group or the entity, and it's also changing based on time, right? So it's Riverside Unified School District, I think is what it is, in 99 and 2000, right? Then there's Redlands School District in 99 and 2000, right? So and they're going to have certain characteristics or certain values of X in those different years. They're changing over time. And there's going to be a particular outcome that's associated with that entity and that time period. So that specific entity is denoted with an I, and then that specific time period is with a T. And so if you remember last class, it kind of felt natural to think of like, yeah, we've got this time period before and after. Now we can just turn them into years. That entity was just one group or another, control or treatment. That can be multiple entities, right, along, say, something like school districts, okay? And so I will run from 1 to n just like it did before, and T will run from 1 to T just like it did, well, not like it did before, but that's what it will run from, right? And then the number of observations in total is just n times T. Okay, and you saw that coming up when we were looking at the 50 states over 3 years. Okay, so let's draw this out kind of by hand just to see what this is going to look like. Like I said, we'll bring up a bigger data set in just a second, right? But let's imagine that we have our school district data, right? And we've got school district 1, and we've got the year equal to 1999. We've got a student-teacher ratio of 22, and then we've got a test score equal to 700. Okay. But if this is going to be panel data, well, what's going to happen is that we're going to have more than 1 year worth of information for school district 1. We'll also have school district 1 in the year 2000. And in that year, their student-teacher ratio was 24, test score was 720, right? Let's say that we've got one more year, 2001, and we've got 21 as a student-teacher ratio and 710 as that test score, right? We can do the same thing for District 2, right, for 1999, 2000, and 2001, right? And let's say that their student-teacher ratios are 25, 24, and 22, and their test scores are 640, 660, and 690. Okay. So what you might be noticing, right, between these two districts, right, is that, well, there's the student teacher ratio. It's hard because you match up right here at 24 and then you match up at 22. There's 21 versus 25. That's really the only difference. But it's certainly, so it's hard to kind of say there's a big difference in student teacher ratio, but this kind of 700 to 720 is definitely higher than this 640 to 690. 690 almost might be an outlier here, right? This school district might be more prone to have 640, 650 as their average, right? Versus the 700 plus for District 1, right? So these right here are going to be just inherently higher scores, right? Where right here, these are just inherently lower scores, right? And so if we were to just look at these two districts, would we say that these two districts are just the same? Gosh, no, there's something just inherently different. The student teacher ratio, again, you can split hairs, right? But they don't look drastically different. District 2 does seem to have lower scores than District 1. So just summarizing what we see here, we see that there's something inherently different, right? Inherently different about District 1 versus District 2, okay? Now, what would be really nice is that if we were to run a regression, it would be nice to capture that inherent difference, right? So what we want to do is we want to capture this inherent difference, okay? So that kind of is setting the stage for what panel data will allow us to do. Now, I'm going to give you another example here and kind of ask you guys to take yourselves back to high school and think about, let's imagine that you're running a regression. You're interested in the number of football wins in school I in year T. And this example came from our first year when we were at Xavier in 2010. We actually lived in northern Kentucky, as we've said before, if you've had us before. And we were driving down the road one day in the fall, and we saw a sign that said like state champs 2008. And then there was another sign that said like 2006, and then 2005 and 2002, right? And they kept going and going. It went on for like 2 miles. Like this school district that we had moved to had been state champs for like, 20 of the past 50 years, all the way back to like 1950. It was just like, wow, they really care about football. It turned out that Chris Collinsworth, the NBC announcer, actually like lived in the city, and he sometimes coached on the football team, right? So there's you think about you guys might have your own schools out there, right, or your own high school experiences where like remember that school that they were always just good at that. They were good at track. They were good at the scholastics, right? They were good at mock trial or something like that. Like some of those schools just have this inherent mock trial amazingness, and you're like, where does that come from? It can't necessarily be like taught completely, right? Just like football players, right, or basketball players, like tall basketball teams. Like, where does that come? It just seems like there's something inherently different, right, about all of these schools that can somewhat explain this. So, if we were trying to explain the number of football wins in District I at time t, one of the things that seems to matter, and again, especially if you've went to like a football crazy district, is like the attitude, right? Is the attitude. And then there's other things, right? There's certainly other things. There's resources, things like that. And I'll just call it other. And notice how I've written this, right? Notice how I've written this, right? So we could run a regression of the number of football wins on a constant beta 1 times the attitude, right? Or that inherent difference. right, towards football, plus beta 2 times other plus UIT, right? So that error term that's going to differ based on the entity in the year. But here, I have dropped the subscript T. Why would I do this, right? Why would I do this? Well, what we can think about here is that attitude, right, towards something like the test scores, towards something like the number of football wins, these are not necessarily changing every year. There's just kind of this like something inherent about that school, about that district. And as long as we're on the topic of football, I happened to drive through Knoxville, Tennessee that same year during their first football game at the University of Tennessee. They were playing like the worst team in the state. They won like by 70 points, but the whole town like shut down for that game. I'm like, they're gonna win. They like stopped playing starters after like a quarter, right? But there's just something about that attitude that's just the same year after year after year. And so something like attitude is constant over time, right? It does not change from year to year. Right? It doesn't change from year to year, right? So we can just drop this subscript T because we could say, I don't know how you measure attitude, right? That's not what I'm getting at right now, right? But you could say attitude is measured from 0 to 100, right? And if the attitude towards football wins is 75 for a district, it's not going from 75 to 95 back to 50 on a year-to-year basis. It's kind of just like 75, 75, 75, right? So we don't need to think of this, what is the attitude for district I in year 1, year 2, year 3? It's just the same the entire time. So that attitude, we drop that subscript T. So because we observe multiple entities over multiple time periods, this means that if we observe a change in the outcome, it cannot be caused by a change in attitude, right? And I'm going to write attitude here. My computer is mirroring slowly today, so I can like watch myself write this out. It's a little awkward, right? But if we observe these entities over multiple time periods, we can see a change in the outcome, like say a change in the number of football wins. But this cannot be caused by a change in the attitude. And I have attitude in quotations because I'm just thinking of attitude as almost this universal measure that doesn't change over time, right? So if you're feeling more comfortable with test scores, right, you could say, hey, that attitude towards doing well on tests in District 1, that's not changing from 99 to 2000 to 2001. Same thing with District 2, right? It's just not changing, right, over that 3-year time horizon. So if we see a change in this test score, it can't be because all of a sudden they stopped caring about tests or did start caring about tests or something like that. Same thing with football wins, right? They're not suddenly changing how much they support the team just overnight. So when we see a change in the outcome, it's not going to be caused by these things that are fixed, okay? So that's ultimately what we're going to be trying to do. Like, you can kind of see with panel data, we're going to try to, parse out what we can actually learn or what we can actually get out of having multiple entities over multiple time periods. And it really comes down to this. If we observe a change in the outcome, we know that that change can't be caused by things that aren't changing, right? Because we're seeing the same thing over time, okay? So our true example, right, our actual example, not our made up one. I mean, it's sort of made up, but I think you guys are all probably remembering back to those schools that had like certain, what about the band school? Wasn't there always like a school that was good at band? Like they always won like state band championship or something like that. Like, where does that come from, right? It's like they're really digging the band, right? Which is cool. That's all great. It's just not like all of a sudden like something changed about that school, right? It was that's kind of something that's inherent over time. So what we're going to look at is we're going to look at traffic fatalities and alcohol taxes. So again, we're not going to get through all of this example. We're going to get through some, I think, important and relevant parts of it, and then you'll have to come to 108 to see the rest of it, right? But this is really showing us how papers originate, okay? And so the first thing we want to think about is what's the motivation for something like this, all right? And the motivation is really steeped in policy because 25% of the approximately 40,000 fatal accidents per year, right? Fatal accidents per year involve alcohol. Okay, so that's one thing, right? And it's just this. It's like a stylized fact. It's not saying that alcohol did or didn't cause anything. It's just simply saying, look, 25% of fatal accidents involve alcohol, and then we also know that from surveys that 25% of drivers on the road between 1 and 3 a.m. have been drinking. Okay. So again, you can kind of sit around, look at these statistics. I know you guys follow lots of different things in terms of just information coming at you, right? And so you start to, I know, as much as we don't want to admit it, we take a lot of these things that we see in class and we start to apply it to what's going on just in the world around us. And you might say, if you see these two statistics, right, can the government enact policies that discourage drunk driving and reduce fatal accidents? Okay. Now, as if you guys have had me before, and even to some degree in this class, like I'll often ask leading questions and say, can we match the data with this or that? Here, this is where research really comes to light, because we can ask this question. It can be kind of a leading question, and we can sit and we can chat about it. But in order to really get that answer, we need to go get some data, right? So going into research, you don't know the answer to the question, right? And we can sit there and say, sure, like if we ban drinking, that should discourage drunk driving. I should put drunk driving here. Sorry about that. All right. Drunk driving and reduce fatal accidents. Yes, yeah, sure, we might reduce drunk driving or discourage drunk driving. We might reduce fatal accidents, but we might not. I don't know. We would like to see if there's something out there that can help inform us about whether policies actually exist that have done that. So what we're going to do is we're going to go out, and like I said, we're going to go get panel data that gives us the fatality rate per 10,000 people, right? And this will be our outcome, YIT. And then we're going to have a beer tax for every state. That'll be our X, every state I for time period T. And we're going to get data on all states from I equals Alabama to Wyoming. There's going to be no Alaska or Hawaii, right, in this data. And it's going to be from my childhood, 1982 to 1988. Okay. So where do we get this data, right? How do we actually get this data? Well, all we're going to have to do, and while this is coming up, I guess that's kind of cool. You can look at this while I watch my gosh, that iPad is just moving so slow today. At any rate, all states in the continental U.S. from 82 to 88. That's going to be your auto fatality data in chapter 10 of your textbook here. And so what you can do, again, I encourage everyone to always just get a sense of the data, what it looks like. I'm having trouble opening that. Yeah. So that's fine. Let me try it one more time. So I get a brute force open this. There we go. See, that's see, I was clearly born in the 80s. We just keep hitting things till they work. So there we go. Okay, so we've got the state traffic fatality data set. We got the number of traffic deaths per 10,000. We've got a lot of information here. Okay, we've got the state, and it's going to be coded with a number. I think that's always helpful. We've got the year, spirits consumption, unemployment rate. We got a bunch of stuff. We got percent Mormon. That's important because in Utah, right, a lot of people are Mormon. Bree's from Utah. We go back and visit her family. You'd be shocked at the number of coffee shops there. Like, I mean, people are lined up out the door for Starbucks, and I'm like, you're not supposed to be drinking coffee. All right, we're the same. What are we looking at though? We're going to look at the beer tax, right? Tax on a case of beer. That's going to be our XIT, and then we're going to have the vehicle fatality rate that I'm going to adjust. I'm going to multiply by 10,000, so that it's just easier interpretation. So that's our data right there, right? That's kind of the code book, and that's helpful to see. Let's go ahead, and I'm going to just go ahead and I'm going to save this, and I'm going to save it into my folder right here. All right, we know that folder. All right, so that's in there, and then I'm going to open up Stata here, and let's go ahead and take a look at this data because this is new data for us, right? This is new data for us. So so start that do file. All right, that do file is over here. All right, going to change our directory. Like clear, change our directory. All right, there. And then use fatality.dta. Then we'll cap log close, log using lecture 17, replace, and then sum and log close. Okay, so let's go ahead and just run that. And we got a lot of stats in here, but I really want to highlight the data. Right, what does this data actually look like? So this is, again, it's hopefully what you would expect, right? So what we see here is we've got Alabama, right, in 1982, 83, 84, 85, 86, 87. Same thing with Arizona, 82, 83, 84, 85, 67, right? So we've got the information on each state, right, all the way down to Wyoming here, right, for each year, 82 to 88. We've got 336 observations, right? We've got all this data here. Notice, and we were pointing out the Mormon percentage, right? You can just guess that this state right here has got to be Utah, right? Because we're in the 60%, right? And then Vermont, 0.28, right? So you kind of know everything seems to be checking out, at least on that front. But then beer tax, right? Kind of beer tax is, we can go ahead and just actually sum beer tax. I know it's up there on the screen, but just to isolate it, we got 0.51, right, or 51 cents for a case in terms of a tax. But that's as low as 0.04 and as high as $2.72. So we got a fair amount of variation there. And we can start to think about, geez, there might be something inherently different about the way that governments feel about beer tax, right? Same thing with the motor vehicle fatalities, right? So let me make sure I get the right, bring that up there. It's MRAL, yeah. So some MRAL. All right, so I'm going to adjust this, multiply by 10,000 here, just so it's a little bit easier to interpret, right? But we got 3 zeros and 2, but the minimum is 4 zeros and 8, and 3 zeros and 4 as the max there. So we have a large spread there, and almost a whole order of magnitude higher from the lowest to the highest. So a lot of variation on that front as well. Okay, so first thing, right? Let's go out and let's just take a snapshot, right? Let's go ahead and take a snapshot of the fatality rate versus the beer tax in 1982, right? Okay. So in order to do that, right, I'm going to do a couple things, right? First, I'm going to just say, let's adjust MR all, or by 10,000, right? So I'm going to just go ahead and replace that MR, motor vehicle fatality rate for all, equal to MR all times 10,000, right? Again, just to make it easier to interpret, we don't have so many zeros to deal with, because again, it won't matter, right? In terms of the magnitude will just change, but the actual numbers will not, or the significance. Okay. And then let's see, what else do we want to do? Let's go ahead and just regress MR all on beer tax, right? If the year equals 1982, comma, robust, let's start an outreg 2 using lecture 17 and replace, right? So we won't really worry about turning into a Word document yet because we just got one regression, but let's take a look at this, right? And let's interpret this. So it's 1982, all right? We've got this motor vehicle fatality rate. So we've got the fatality rate hat for each state, but now that time element is just 1982, right? It's just 1982, right? And then we've got beta 0, which is going to be 2.01, right? 2.01. And then that's going to be significant, highly significant. And then we have plus 0.15, which is, it's not quite significant, right? Not quite significant, but it's positive, right? Times the beer tax in 1982. Okay. So again, the year is 1982, just one snapshot that's essentially saying what, right? We can interpret this coefficient in the same way we'd interpret everything else. So the question came up about, like, is this cumulative? Like, I think it's a good place to start, right? It's just kind of going back to what we started the whole term with. Now, before I do that, I actually want to show what this looks like. Like, we've got a positive relationship here, and that might be that doesn't seem necessarily right. So let's see what this scatter plot looks like to see if in the LFIT, the regression line, see if this makes sense to have this coefficient be positive. And I'm kind of letting you stew over it and think about it a little bit, right? But what does this scatter plot look like here? Right, it's coming. Well, there's that insignificance there, right? We have a lot of error, right? This would be a great example of heteroscedasticity as well, right? Even though we got robust standard errors, well, we do have robust standard errors that's adjusting for that, right? But we can see a lot of variation here, right? When the taxon case of beer is low, right? But then as it goes up, we don't have that many observations, but we also have a lot of variance in our error term as well. So if we think about this interpretation, right, beta 1 equaling 0.15, this is telling us what? Well, it's telling us when the beer tax increases by 1 unit, so this would be by $1, right? The traffic fatality rate increases by 0.15 per 10K on average. But that seems, it's insignificant, right? So, but on the surface, this point estimate is literally telling us that the beer tax going up increases the fatality rate. This doesn't feel very right, right? There's something that feels wrong about this. So the thing that we could do is we could say, so higher beer taxes, more traffic fatalities, question mark. is what I'm writing here. Now, we could ask ourselves and say to ourselves, well, maybe this is just an anomaly, right? Maybe this is just that it's just that we have this 1982 as just this weird year. So perhaps what we need to do is just look at another year, and let's look at the last year. And so what I'll do is I'll go ahead and just say let's regress MRL on beer tax if the year equals 1988. Robust outreg 2 using lecture 17, and then let's go ahead and do comma word. The other thing I want to do is let me go ahead and make that scatter plot, right? So we can just have both those up at the same time and change these to 1988. Okay, so run that, and let's see what we get here. So first one comes up, second one comes up. Looks about the same, if not even more upward sloping, right? And in fact, that's exactly what we see now. It's significant, right? So in 1988, well, we have fatality rate in state I in 1988, all right? Equal to, well, the constant that's not as important. I mean, it's not irrelevant necessarily, 1.86. But this is going to be that average fatality rate when the beer tax is 0. But that no states have that, but it's also not unreasonable to think that they may have a beer tax of 0. But then plus 0.44, and that's going to be significant there, times the beer tax, state I in 1988. Okay. So beta 1 equaling 0.44 here has the same interpretation as the previous regression in 1982, right? That we've got higher beer taxes, more traffic fatalities. But let me present it to you in this way, right? Instead of saying it like we have, we could say that states with higher beer taxes have higher traffic fatality rates on average. Well, when you say it that way, that doesn't seem as unpredictable, right? So when we first ran this, I think, kind of just the way that we were kind of just generating this is that, hey, if you charge people more for beer, you should have less drunk driving, less traffic fatalities. But because we're looking at just a snapshot, right, what we're finding is that states that have these high beer taxes right here tend to have higher traffic fatality rates than states down here that have lower beer taxes, right? Why is that the case? Well, maybe there's something about the attitude, whether it's towards driving or drinking or both or whatever, right, that may be causing both of those things to happen at the same time, right? So what this ultimately points to is that and again, this is kind of going back to the early material of the class, but it's not as, it has a different feel to it now that we're at this stage of the course. The expected value of u given x is probably not equal to 0, all right? Because it's essentially saying, look, those states with higher taxes on beer, well, they might have a certain propensity for beer. Let's go back to Utah. Should Utah have a high, if they want to generate revenue, if that's what this is for, right? If they want to generate tax revenue, should they be taxing cases of beer? Boy, I mean, if people are really adhering to, the religion there, probably not. They should probably tax like they also have these drive-through fizz drinks is what they call it. Like it's just soda, and it's just like these lines are backed up too, right? It's just like give me the sugar, replace the alcohol with like a ton of sugar. So taxing beer wouldn't make a lot of sense there. But there's also probably not a lot of as much drunk driving as in some other states, for example. So because of this, right, the expected value of u given x not equaling 0, it seems really clear that this beta 1 hat that we're estimating is not equal to the true beta 1, right? There's some sort of bias in our regression when we just take these snapshots. Okay. So then the question becomes, okay, well, let's really contextualize why this might be the case, right? So why does this bias exist? What are we picking up here? Well, just as I alluded to, all right, let's talk about the cultural attitude towards drinking and driving. Okay. You may have been to certain places around the country, or even within a state, but again, kind of more spread out. You could say there's some places where it's a big deal versus no deal, right? And we could imagine that in places where that attitude is fairly strong, right? So if we said that the attitude is a determinant, right, of say something about like if you're willing to drink and drive, if that's a very prominent attitude in the environment, right, among drivers, right, that's going to potentially increase fatal accidents, right? But that's also going to be maybe related to drinking and maybe a source of revenue for policymakers, and maybe something that they'd say, oh, we also want to reduce drunk driving, right? So we would say that attitude is a determinant of fatal accidents. Yeah. So in that case, we can think of it as part of UI, right? That's how we would ultimately think of this, right? Is that error term that comes from this fatal accident rate, partially driven by attitude towards driving. Now, the question then becomes, is that attitude that we've thought about earlier in the class, is that correlated, right? Is that correlated with beer tax? Okay. Well, potentially, right? That makes sense that it could be. There could be this correlation between our beer tax XIT and we'd say UIT, right? Because if we're not controlling for attitude, it ultimately goes into that error term, right? So if we say if we are not controlling for attitude, it becomes part of the error term. So what this essentially is pointing towards, and we see it literally up on the screen here, is that if we don't control for attitude, we have omitted variable bias, right? We have omitted variable bias. Okay. So we've got this scenario, which I think everybody can feel okay with and can kind of say, all right, I'm kind of seeing this here. Whether you have your own experiences or can just kind of come up with one, we can think about this situation where attitude is strongly related to just driving behavior, and then also something about drinking and driving at the same time, and by extension, the beer tax. So what we need to do is we need to figure out a way to use the data that we have to control for something like attitude, even though we don't exactly know what goes into attitude. Because you might be sitting there saying, like, what do you mean by like attitude? Like that could mean like 1,000 different things. Yeah, it can mean a million different. I mean, we can keep going on and on and on, right? But ultimately, if we don't control for something like this is like perfect timing as I'm delayed here. We're going to have omitted variable bias. Okay, so with that in mind, we need to figure out a way to control for attitude without knowing what goes into the variable. Okay, so I'm writing out, we need to control for attitude without knowing what goes into the variable. So what I'm going to do here is I'm going to propose a slightly altered regression of what we just had. So I just ran the fatality rate on beer tax in 1982, right? But what I want to do now, gosh, this is like painfully slow. Hold on. It's like still painfully slow. Like I'm not, boy, if I wrote this slow, can you imagine how, man, class would be so boring. So I'm like sitting here waiting for it to end. So yeah, so we got to control for attitude without knowing what goes into it. So the regression that we can run and describe here is we can have the fatality rate. And so this will come up here. Man, that is slow. But then, when I move it up, it's going to move really fast. Here we go. There we go. All right, so I'm going to look at the fatality rate in state I in 1982. Okay, so this will be our actual specification. Okay, and this will be equal to beta 0 plus beta 1 times the beer tax, state I, 1982. Okay, so that's what we ran before. But then what I'm trying to get at with this attitude is that this attitude can be described by zi, right? So just some variable zi. I had it as attitude I before, but now we can think about there being this zi, which is just representing that attitude, right? It doesn't have an index with time because it's the same year after year after year, and then it's just got some beta 2 attached to it. Right, so again, think of that attitude as running from 0 to 100 for different states, and there's some beta 2 attached to that, right? And then we have plus UI 1982, right? So we don't want to forget that error term. So what I've done here is I've essentially separated out what goes into that error term into something that's fixed, that doesn't change over time, ZI, and something that does that's essentially attached to 1982. Right, so there's something about maybe the weather in 1982 in a certain part of the country that caused the fatality rate to be higher or lower, something like that, right? But then there's also something like attitude that isn't changing over time. So what ZI is representing is a variable that impacts the fatality rate in state I, fatality rate in state I. Okay, so I'm going to let this right out here. So it can impact the fatality rate in state I, but it's not changing from year to year, right? But does not change from year to year. All right. Okay, so that's why we take that time element off that, because that attitude, and that's something like football, like you can talk about whether that's attitude's going to change over time. And again, we can debate the same thing here, but it really seems difficult and a hard argument to say like all of a sudden that attitude towards drinking and driving is going to change suddenly in one single year, or that the driving behaviors, the way that people do drive. So we spent a lot of our summer up in Oregon, and it's funny because you can see the different attitudes in driving behavior between a place like Oregon and a place like California. And so like in Oregon, like the fear of the right turn is hilarious. It's like somebody will have their blinker on, they'll be turning right, there'll be like nobody around, but it's like coming to like a complete stop. And I'm like, am I missing something? I'm like looking around like there's something wrong, right? But then you go to California, and the thing that I noticed here, you can kind of get on drivers everywhere, but what Californians like to do is, they've got these wide lanes in California, but they are used completely. Like there is a lot of drifting. It is like you have a lot of time to text on your phone and drift before you actually leave the lane in California. So it's funny, like as soon as we got back down into California, it was like, there's so many cars around us, right? So the thing about that, though, right, those types of behaviors, right, that attitude, and so whether you want to think of it as attitude, driving behavior, whatnot, whatever example you have that differs across states, but is constant within a state over time. Right. So it wasn't like we got back to California and we're like, oh, I can't believe everybody's drifting. It's like, no, I guess they were always drifting, right? And they're going to drift next year and the year after, and that's just the way it is. And so we would consider that to be part of ZI. Now, I don't exactly know what goes into ZI, especially in 1982, right? But we can start to think of those things that just impact the fatality rate, but don't necessarily change from year to year, right? Probably the most poignant example, and actually, and we'll go through it here when we add the next regression, and I'll say, yeah, I'll wait. I'm going to hold off on that example because I think it's going to make this really clear. We can go ahead and run this same regression in 1988, and what we'll notice here is that the beer tax in state I is going to change between 1982 and 1980 for most of the states, right? You're going to change for most of those states. Because if you imagine we laid the two graphs on top of each other, right? We'd see dots at different parts on the x-axis here, right? But that attitude is not changing. So we're still going to get beta 2 ZI. And then we'll have UI 1988. Okay, so just finishing that off. So here, again, beer tax can be different, fatality rate can be different, the value of UI, right, is going to be different, right, between 82 and 88. But what we're doing with ZI is we're saying, look, ZI by definition is not changing. So a good example of that when we're thinking about roadways is actually like the roadway itself, right? So if we think about I-5 and like the curvature in I-5 or I-10 or something like that, or 91 and 215, right? That intersection is not changing over time, right? It might cause a lot of traffic, might cause a lot of congestion, but it's not changing the look of it, and what it could do to driving behavior is not changing from 82 to 88, right? It's fixed over time, but it could change. Like the intersection in California, the intersections in California are going to be very different from a place like Oregon or Montana or a rural state, right? And that's going to be captured with ZI, all right? So I think that's kind of a nice way to think of ZI. So what we want to do is we want to be able to control for ZI. How can we control for ZI? Well, all we need to do, if we look at this mathematically, is subtract the fatality rate in state I in 1988 from, or we'll do that, and the fatality rate state I 1982. All right, we can just look at that difference between the fatality rates in those states in those 2 years and know that ZI can't be the reason that those things differ, right? So to just see this mathematically, right, the fatality rate in state I in 88 minus the fatality rate in state I in 82, this is going to be equal to beta 0 plus beta 1. We'll put tax I 88 plus beta 2 ZI plus UI 88, right? That's going to be our fatality rate regression in 1988. We're going to subtract this from, I'll put that in parentheses there, and then subtract it from beta 0 plus beta 1 tax I 82 plus beta 2 ZI plus UI 82. Okay, so that should be coming slowly here. I don't know why. It's driving me crazy here, but it's okay. Right, so just writing the same regression just below it, right? It's like we can watch this together, right? You got 82 coming, and then beta 2 ZI is going to be the same, right, in both scenarios, right, by definition. And again, you may be saying to yourself, well, what if something changes? If something changes, it ain't part of ZI, right? It wouldn't have that no time element on there, okay? So when we take this as a whole, we'd say, well, the change in the fatality rate between state I and state I, between 82, 88, well, what does that equal? Well, beta 0 should go to 0. Beta 2 Z1, this should also go to 0. So we're left with beta 1 times tax I 88 minus tax I 82 plus UI 88 minus UI 82. Right, that's what we're left with. We've essentially eliminated that ZI term from our regression by just looking at the change in the fatality rate. So if we do change in the fatality rate, so instead of writing all of this out, I can do change in the fatality rate in state I is going to be equal to beta 1 times the change in the tax in state I plus the change in UI. So what have we done? We have removed ZI from the regression. And the reason that we've removed it from the regression is because we know that any change in Y cannot be caused by a change in ZI. And I think that that's really slick, right? That is just really, really slick. Okay, so let's do this, right? Let's actually make this happen because we can actually let the writing keep going, right? We can go ahead and say, let's regress, right? And make this a little bit bigger here. And let's regress the change in the MRL on the change in beer tax between 82 and 88. So the first thing I want to do here is I want to just clean up my data a little bit. So I don't ever recommend doing this. This is just for instructive purposes. I want to get rid of everything between 83 and 87, just so it looks cleaner. All right, just so it looks cleaner. So what we can do is we can go ahead and we can say, let's keep first our state, our year, our MRL, and our beer tax. So I just want to first keep the variables that I'm going to work with. Again, I don't recommend doing this. This is just, again, to help keep things clean. All right, so I'm going to run this do file here. Do that there. Come on. Oh boy. Notice the lack of panic. Little typo there. There we go. So let's take. I was like, I don't know why. Where's my? I want my data to leave. So I've got year, beer tax, MRL, and state. And notice that the states are labeled with the actual coding of the states, but then they're actually attached to numbers up here. They're actual bytes. They're not string variables, so they're not read. So again, this is just a labeling notation here. So we've got state, we've got year, we've got beer tax, and more MRL, right? But then the other thing I want to do, like I said, is I want to get rid of the years that are between 82 and 88. So I want to keep if year is greater than 1982 and year is, or sorry, I want to drop rather, not keep. I want to drop, and if year is less than 1988. So just drop those years that are in between those endpoints. So the reason I like to do this is I like to show you guys, hey, this is what the data is ultimately. We could do this in bigger pieces, but we can say, all right, let's look at, or smaller pieces rather. We do just one big shot here between year 1 and year 2, 82 and 88, 82 and 88. What we want to do is we want to take the difference here, difference in motor vehicle fatality rates, and the difference in the beer tax. And so what we would say is that in Alabama, notice here that the mortality rate went up a little bit from 2.12 to 2.49. The beer tax went down from 1.53 or 1.54 to 1.5. That increase, maybe that's because of the beer tax, maybe it's not. It's certainly not because there was some sort of big infrastructure change or the way that people drove in Alabama changed all of a sudden. right? We can rule that potential out, right? And say, yeah, we're controlling for those things that aren't changing between 82 and 88. So what we need to do is we need to generate a new variable that gets at that change, right? And so this is just some more notation. This is kind of, I think, helpful and interesting, but we need to create a change in MRL and beer tax, right? So how would we do this? So what we would say is we want to do this by state. So by sort each state. What we want to do is we want to generate a change in, we'll do beer tax first and say that's going to be beer tax for that particular year. So underscore n says, yeah, so you can almost think of it as we have the states going from observation 1, 2, 3, 4, and they're just indexed by n. And we're going to subtract it from beer tax underscore n minus 1. And so what that's going to do is that's going to take the difference in the beer tax between, say, 82 in the previous year we don't have any previous year for Alabama, so we shouldn't get anything. Then we're going to do 88 from 82, right, or 82 from 88, and we should get -3 cents, all right? Shouldn't get anything in 82 for Arizona because there's no observation before 82. 88 minus 82 looks like we've got a 13 cent increase or something like that, right? So let's see this generated. Exactly what we expected. We got our 3% reduction, or 3 cent reduction, 4 cent reduction, then with 13 cent increase, 12 cent decrease, right? So we can see that difference there for each of those states. And again, we're missing out on 1982 because we don't have any observation before. There's no change from a prior period, okay? So do the same thing for that fatality rate. So we'll say by each state, by sort state, let's do the change in MRL on MRL underscore n, right, for that particular index there, indexed in that particular year, right, minus MRL brackets underscore n minus 1, okay? And let's see that created. There's our increase of about, I said it was going to be 0.4, 0.3, okay? Or 0.36, 0.37, right? So now, when it comes to running this regression, all of a sudden, this regression becomes really straightforward to create. All we've got to do is regress the change in motor vehicle fatality rates on the change in the beer tax, and we'll do comma robust. We only got 1 year of this, right? We only got 1988 is our year, right? And then we can go ahead and outreg 2 using lecture 17 Word, right? And let's create this thing. I can just run the whole thing again. I don't want to have a nice no red mark outcome here. We can go ahead and open up this Word file here. So it's funny because like Stata's running, I think it's the mirroring program that's really hurting this iPad projection here. But okay, so what do we get here, right? Let's interpret this. Let's figure this out. We've got a change in the fatality rate. We'll put a hat on there. This is equal to, well, we've got actually a constant, but notice how much smaller this constant is, right? This is like the first constant that we've had that's actually insignificant, right? We've had so many significant constants, right, over the entire term, but here we kind of expected that constant to drop out, and it did, right? It's we can't reject 0, right? It's 0.060, it's negative 0.07, and got a 0.065 standard error, right? So we can't rule out 0 as a possible value of beta 0, right? But then we see this negative 1.04, and we'll put a hat on there, and then we can go ahead and have our 0.35, so pretty significant, times the change in the beer tax. Okay. So how do we interpret this? We would interpret this beta 1 equaling negative 0.104 as an increase in the beer tax of $1 in a state. That is really important, right? So we're increasing the beer tax by $1 in a state, not just a higher beer tax across states, right? The state itself has a $1 increase in the beer tax, right? So increase in beer tax of $1 in a state is associated, right, with a reduction in fatality rates of 1.04 per 10,000 on average. Okay. So here, right, if we have a large change in the beer tax, we're going to see fairly large change in the traffic fatality rate going down by 0.1 per 10,000. Oh, sorry, that should be, is that right? Oh, I just did this wrong. I'm sorry. I got decimal excited. I don't know why one would, but apparently I did. All right, 1.04. Sorry about that. Yeah, that looks good. Okay, so we can see here that we've went from a situation where we had this positive and significant coefficient, and we felt like that might be biased, and now all of a sudden we've got this negative and significant coefficient, because what are we doing? We are controlling for ZI. This caused beta 1 hat to go from positive to negative. There's no way we would ever say, hey, we've got this negative or this positive relationship between beer tax and fatality rates. We should probably reduce the beer tax and everything will be better. No, here we're saying, look, within that state, if we increase that beer tax, we're going to see that motor vehicle fatality rate go down and now that we've controlled for these ZIs, right, these attitudes, right, we see this beta 1 hat go from positive and significant to negative and significant, which is what we expected, right, if we were policymakers or advisors. So this is a great stopping point, because what we're going to do to end the term is we're going to extend this to more than 2 time periods, right? You might be saying, can't we just utilize all of the time periods, and can we do something with that? We absolutely can. That's exactly what you were asked to do in your lab, so that's going to all come together for the last hour of the class, of the term. So with that, I'm gonna let you guys go. You guys stay an extra minute. I'll give it back to you, or whatever. You know, you're good. You're good. Enjoy your day. Just keep hanging in there. Know that we're just kind of hanging out in this class. There's not too much left. Do your lab, lecture quiz. Maybe wait till after Thursday to do that, but you'll be all set. You'll be all set. So enjoy the day, guys. Stay safe. We'll see you on Thursday. See ya. Thanks, guys. Thank you.
Hey, Professor, what is the final exam time?
I think it's at 8 o'clock.
It's December 8th or 9th?
8th.
8 o'clock, 8 in the morning, right?
That's right.
Okay, thank you. You have a good day.
No problem. Have a good one.